Welcome back, ladies and gentlemen. We're going to be continuing our discussion about phase change. Today we're going to be talking about heating and cooling curves. So a curve is just the fancy general way to say a graph. So here we could see a heating and cooling graph. And what we notice, of course, is that we've got temperature here and we've got some strange unit down here. This is energy. So what we're going to be talking about here is how temperature and energy are related. Now, in the previous videos, we've talked about how in order for us to change from one phase to another, we have to give enough energy to the particles so they can overpower the intermolecular forces. And what we can see here in this very quick graph that we see in front of us is that when we are changing phase, right, here's water, right, and right here we can see this, right here is water, right, freezing or melting, and up here we've got water turning into steam. Right? Because that's at 100 and at 0, respectively. Well, what do we notice? There's a flat line there. That's very strange. We've sort of talked about this. We've alluded to it, but now we're going to talk about it in more detail as soon as the slides move forward. There we go. So heating and cooling curves. To map the energy and phase of matter, we use a heating and cooling curve. Shocking. There it is. Right? This is our water heating and cooling curve. How do we know? Because this is at 100 right here, and this up here is at 100, sorry, and this is 0. A change in temperature, A, C, and E, right? This is changes because they've got a slope, is really a measure of the change of kinetic energy, or how much the particles are moving. The more the particles move, the more kinetic energy they have. But when molecules are trapped by the intermolecular forces, they can't move, and yet the energy is still increasing, B and D. Well, where is it going? Okay, so what do we mean by the energy is increasing? Well, over here, we have an increase in temperature, right? Because the graph is going upward. But at B and D, the energy is still increasing, right? We're getting more and more energy, but the temperature isn't going up. It's staying the same. So that's super weird, right? Because I'm adding energy, but nothing is increasing in temperature. Now remember, temperature is motion. So what we're saying here is that I'm adding energy, but the energy isn't moving. It's doing something else. As the energy is banked in preparation for breaking free of the intermolecular forces, we won't see an increase in temperature, but there is a change, a phase change. We call this increase of stored energy potential energy. I mentioned that in the last video. Here we are talking about it a bit more. Potential energy is what happens when we store the energy in the particles. And what's happening here, to get a little bit technical, is that as we're storing the energy in the particles, right, as the energy is being stored in the particles, it's like the particles are being paid for their job, and then they're taking the money, and instead of spending it right away to move, they're taking it to the bank and they're depositing the money. Okay, so as they deposit the money, their overall wealth, their overall energy is increasing, but the amount of energy that they have right now to spend on things, to move, doesn't increase. Now, the reason they have to bank all this money is because breaking free of the intermolecular forces, overpowering the intermolecular forces, it's kind of like you got to pay down a debt, right? Like you owe me $10. So every day you come and you give me $1 until finally you've paid off all the money you owe me, and then any other money you make is now free for you to use, free for the particles to move. So potential energy here for the breaking free of the intermolecular forces, that requires you to sort of pay off this debt that you have to the intermolecular forces. And that requires a lot of energy, but the energy isn't used for moving, not right away. So that's super weird, but that's what's going on. So what we see here, right, is so on our curve, only one type of energy change can occur at a time. Either we have kinetic change or a potential change. So kinetic changes means that the particles are going to move faster. So you go from your like 10 degrees Celsius to your 20 degrees Celsius, right? That's a kinetic change, right? The particles are richer. A potential change means that you end up with some sort of like particles changing phase. So you get a liquid going to a gas, right? I've gone from, instead of going from 10 to 20, instead of the particles moving faster, they're just paying off their debt. They're breaking free of the intermolecular forces. We never get both at the same time. It's either one or the other. We can sort of see that, right? Because if we look here at the graph, we start off down here at 0, or sorry, at negative 40, so a standard Winnipeg day, and we're slowly but surely getting warmer and warmer and warmer until we hit zero. At zero, we don't get warmer anymore. The particles don't get any faster. Instead, we start to turn the ice into water. And what we could think of, right, is like, again, remember, when we saw the iodine diffusion tube, things don't freeze or melt instantly, right? Some of it freezes before others. So right here, the hottest of all, right, the most energetic particles will melt first, and they'll turn into water, whereas the colder particles will take longer and longer and longer to warm up. Once enough particles have warmed up for the thing to go from solid to liquid, then it starts to increase in temperature again, right? It starts to move faster. The particles bounce around more. Then we get to the liquid-gas transition, and the same thing happens. You'll notice this is a lot longer, too. I wonder what that means. Takes longer to boil? I wonder why. If only we had some kind of unit about gases where we could learn about that. Ooh, foreshadowing the future. So here we're going to do an example, right? It's the same one, it's water, right? So let's take a look here. The temperature rises, the heat is absorbed by the solid, right? So that's happening in A, right over here, as I just said. Then the increase in temperature means the increase in kinetic energy. Next, melt the solid by absorbing the energy endothermically, right? That means we're absorbing energy from the outside. All the energy absorbed by the solid is used to overcome the intermolecular forces that hold the solid together. So they're paying off that debt they owe. The absorbed energy is then converted into potential energy, so it's stored in the particles. Remember, we said that in order for a particle to go from being a gas bouncing around to being a solid, it has to land and deposit all of that energy into the solid. All that energy being this energy we're talking about here, the potential energy. The temperature stays the same while melting because the kinetic energy is not changing during the melting process. So while something is melting, it does not get hotter or colder, right? During a phase change, it stays exactly the same, which is kind of counterintuitive, or at least it feels like it. At point C here, we get to add more heat now and increase the temperature. An increase in temperature means an increase in the kinetic energy, just like before. In part D, so way up here, the liquid is turning into a gas at its boiling point. And then finally E, the temperature of the gas is rising, increasing the kinetic energy of the gas. If we kept going, right, if we kept going up this chart until we got all the way up to the plasma level, we'd see the same thing. We'd have a flat transition here when we went from a gas to a plasma. Okay, so that's what a heating curve is. Here is water's heating curve, right? So we see over here, this is in your notes, but here it moves. So this is the solid ice, and it's basically not moving because it's a solid and it's very cold. Once it hits the melting point, the liquid solid time, you'll see that it's got some solid ice cubes floating around in some water that's already liquid, right? And over time, those ice cubes will melt. Then you see here, this is all water, and the water is getting warmer and warmer. So in theory, right, if they wanted to cut this little animation up into smaller sections, they could say that down here where it's cold, it wouldn't move very much, and over here it would move a lot more. Once you hit the gas to liquid level, you see that some of the water particles start to escape, turning into gas, while some of it stays liquid at the bottom, just like here we had liquid and ice in it. Finally, we're going to get the gas transition, where we get all of this gas bouncing around inside the box because it's super energetic. That's it. That's the basic idea, right? Things don't melt instantly. They don't freeze instantly. They take time. And while that is happening, other things can't happen. It's kind of it, really. Cooling curves are the same thing. They're just backwards. So instead of going from a low number to a high number, we start at the high number here and we drop down steadily through the same basic procedure. You'll notice it's the same, right? Like the flat parts are the same area because water freezes at 0 and it condenses at 100. The size of everything's basically the same, so there's no real difference here, except that now it's going down. Right? And in this case, because we're losing energy. That's all. We're decreasing the kinetic energy or we're decreasing the potential energy in order for this to happen. That means the energy is going somewhere else, right? So these are exothermic reactions at this point. So yeah, that's the basic idea. And you may remember from this slide way back, energy is increasing across this whole transition. So as things melt, we increase the energy. Sometimes it's kinetic, sometimes it's potential. And that's kind of it, really. So at this point, you guys just need to get a little practice in, work through some of these things. There are a few subtle situations. I guess maybe I'll mention them. The size of this length here, this area, the length of this, that's telling you that it's going to take a lot of energy, or it's going to take a long time to cause the transition from liquid to solid, or sorry, liquid to gas. And that's because, well, as mentioned, things we're going to see in the gas phase. But if I have the same size sample in both, if I have two beakers of water and I do the same cooling thing, I should get the same size of this, right? It should be characteristic of the material, an intensive property. Remember that from way back? But if I have two different samples, and one of them is bigger than the other, then we would expect these two graphs to be of different sizes, right? Like if I had some kind of other material, right? Let's say I had another bit of water here, and it was a larger sample, right? So maybe this example here on the graph is me trying to condense and freeze down a glass of water, and maybe I'm going to have another one that's a bucket of water, right? So it's more. So at the same, right? So the cooling down part's the same. But then when I get to the transition from gas to liquid, because there's more of it, it will take longer to cool down. So I'm expecting that this will be longer. How much longer depends on how much more material there is. Then, of course, just like before, I'll cool down. And then now it's going to take me longer again. So much longer, I'm going to go off screen a little bit there. Oh, can we see it? Just barely. And then it's going to go down again. So we'll see that these plateaus, these phase transitions are longer. Why are they longer? Because there's more material to freeze. So it takes more energy. You'll notice that the place where I put the plateaus is the same, right? Like I didn't draw them sooner. I put them in the same spot because water always condenses at 100 or boils at 100. It always freezes at 0 or melts at 0. So the fact that the things were longer had nothing to do with what the material was. It had to do with how much material there was. On the other end, if I get another color out, maybe let's do red. If I was talking about a totally different material, maybe it cools down, and it cools down for a long time, and then it hits 60, and then it only condenses very quickly, and then it cools down some more, and then maybe I'm going to make it freeze at 20, and then it just keeps cooling all the way down like this, right? That transition, which might be I could have made it a little easier to see, that transition there indicates that this is a different material because it doesn't melt, condense, freeze, etc. It doesn't go through a phase transition at the same temperatures as water. So it must be a different material. I mean, heck, in this case, I made it shorter. I could have been very sneaky and just said that it was exactly the same length, and then it came down, and then, let's keep the same material here. And then it was exactly the same length again, and then it came down. I could do that, right? I could make this a sneaky looking little question because it all looks, it follows very similar. It's the same length and everything, but it happens at a different temperature. So what that probably means is that I have the same amount, right? So if I said this one that was originally on the slide is a cup, this could be a cup of whatever my unknown material is. There's the same amount of it, but it's a different material, so it freezes at a different temperature. Okay, that's the basic idea. So at this point, guys, I'd like you guys to do some practice, work through these. There's a lot of practice on this because it takes a little bit of practice to sort of get the hang of it, okay? So try the practice. You have the answers to them so you can see how it goes, and I will see you guys next time.